As we delve into the intricacies of machine learning performance evaluation, one crucial aspect that demands our attention is selecting an appropriate performance measure. Among the myriad of choices available, one measure that stands out for regression tasks is the root mean square error, RMSE. Allow me to take you on a journey through the history of RMSE, its significance, and examples of models that have utilized this performance measure. The RMSE is a metric that provides us with invaluable insights into how much error our predictive model typically makes in its predictions. It holds a higher weight for larger errors, making it an ideal candidate to evaluate the accuracy of regression models. The objective is simple yet profound. We seek to minimize this error and enhance the model's predictive capabilities. To understand the genesis of RMSE, we must delve into the early days of statistics and the quest for better model evaluation techniques. The concept of RMSE has its roots in the mean squared error, MSE, which was a pioneering approach in the field of statistics. The MSE is the average squared difference between the predicted and actual values. However, using squared values can lead to some issues, such as amplifying the impact of outliers, which may not always reflect the model's true performance. In response to this, the concept of RMSE emerged as a more interpretable and intuitive measure. The RMSE calculates the square root of the MSE, returning the average error in the original scale of the target variable. This makes it easier for us to grasp the practical implications of the model's performance. Imagine a model that predicts housing prices based on various features like location, income, and population. We can use RMSE to measure how well our model performs in predicting the actual house prices for a given set of features. By calculating the RMSE, we obtain an estimate of the average error in our model's predictions. A lower RMSE value indicates that our model's predictions are closer to the actual house prices, signifying a more accurate and reliable model. Notations play a vital role in understanding and applying RMSE. Let's break down the notations used to calculate RMS. M, the number of instances in the dataset we are evaluating RMSE on. For example, if we are evaluating RMSE on a validation set containing 2,000 districts, then M equals sign 2,000. XI, a vector of all the feature values, excluding the label, for the ITF instance in the dataset. I, the label which represents the desired output value for the ITF instance. For instance, let's consider the first district in our dataset. We have features like longitude, minus 118.29, latitude, 33.91, number of inhabitants, 1,416, median income, $38,372, and the median house value, $156,400. X will be a matrix containing all feature values of all instances in the dataset, and Y will be the vector of labels representing the actual house prices. When evaluating the performance of our model using RMSE, we calculate the predicted values using our model for each instance in the dataset and compare them with the actual labels. The square differences are then averaged, and the square root of this average yields the RMSE value. Now, let's explore some real-world examples of models that have utilized RMSE as their performance measure. In housing price prediction tasks, linear regression models are commonly employed. Linear regression models aim to fit a straight line to the data, minimizing the sum of squared differences between the predicted and actual values, that is, RMSE. Similarly, support vector regression models, which extend the concepts of support vector machines to regression tasks, also use RMSE for evaluation. In conclusion, the root mean square error, RMSE, is a fundamental and valuable performance measure for regression tasks. Its ability to quantify the average error in predictions, accounting for both small and large errors, has made it a go-to metric for evaluating predictive models. Armed with a deeper understanding of RMS and its notation, we can confidently assess the accuracy and effectiveness of our predictive models, ultimately leading us to build better and more impactful machine learning solutions. Let us embrace this powerful tool as we embark on our journey towards making positive societal change through machine learning.